Next speaker is Will Steinberger. Will, if you want to go ahead and start the share.
All right, hello everyone.
Yep, we can stop that. Wait, yeah, we can see your slides, we can hear you. So Will is a fourth-year PhD student here at Michigan. He's going to talk to us today about extracting neutron spectra using a handheld dual particle imager. Will, please go ahead.
Excellent, thank you very much. So to begin, some background motivation for this. So the NNSA plays a key role in preventing, countering, and responding to radiological devices and potential dirty bombs, things of that nature. For this, emergency responders, warfighters, people of that nature require a low power, compact, lightweight, inexpensive, and durable imager to be able to successfully locate these sources of radiation. To be able to do this, we've proposed a system that we've called the handheld dual particle imager. This is a combination of organic still beam pillars and then some inorganic, in this case one LISO pillar, coupled to silicon photomultiplier arrays to produce a scattered-based imaging system. This works as a combination Compton camera and neutron scatter camera. Now, for the purpose of this presentation, as the title suggested, we're going to focus on the neutron imaging capabilities of this system. And one of the properties of having a neutron scatter camera is that in reconstructing the double scatter events, you determine the incident energy of the neutron. And this gives us spectroscopic capabilities for imaging neutron sources. So one of the questions we posed is, can we both image and then isolate multiple neutron sources that give off different energy spectra and identify the sources by those energy spectra? So before we get into that, let's talk a little bit more about the imaging system that we've built. To give you a sense of scale, I have on the left there a diagram of just the layout of our still beam pillars and our single LISO pillar. And you can see that these fit in an area of about 5 centimeters by 5 centimeters. You can see a photograph of the physical system on the right there in this box that I believe Neural had some pictures of the INL campaign that we attended. But with this system, we look for double scatter events between these still beam pillars to be able to reconstruct where neutrons originate. And to just talk about that, I know Nathan touched on that as well, but here is how our system works. If we have some source where a neutron comes in with some incident energy, scatters in our first pillar, scatters in our second pillar, what's interesting about this system is that we get an output pulse from both ends, from both IPM readouts. And you can see here that with those, I need to move that, these pulses have two different pulse heights and pulse integrals. And based off of the relative pulse amplitude or relative integrations there, we can actually determine where an interaction occurred along each pillar with some degree of certainty. So for each one of these interactions, we obtain an energy deposition, position information, and then timing information. We use all of that information to reconstruct the energy of the neutron. We determine its time of flight energy, E time of flight there. We sum that with the initial energy interaction. And based off of those parameters, we can figure out a probability distribution of where that neutron originated. We call this a cone projection. So now that we have this and our imaging setup, what kind of measurement are we looking at? So in our laboratory, we have a californium-252 source and a plutonium-beryllium source. Californium-252 emits a Watt spectrum, and plutonium-beryllium is an alpha N source. So you can see the plot here on the right that I have. This is comparing a simulated spectra with intensity incident on our system between the californium-252 source and the plutonium-beryllium source. And we can see that the plutonium-beryllium source on average has a much higher spectra than the californium source. Now you notice in the image on the left here, or the figure on the left here, I have the two sources at two different distances. They're separated by about 56 degrees in this geometry, and this geometry is to scale for the measurement we perform. As I said, they're separated by 55.6 degrees, and we notice that the plutonium-beryllium source is much closer than the californium. We did that so that the sources are about the same neutron intensity onto our system. So when we image the source and produce simple back projection images, when we sum all of those cone projection images, we get a relative equal intensity source. And so now the question becomes, what does that look like? So we went ahead and performed this measurement, and we took about an hour and a half worth of data, and we obtained this image here, where we have a simple back projection image where we have know that the californium source is on the left and our plutonium beryllium source is on the right there. And we can see that even in simple back projection, we have these two sources are relatively well separated. So one of the things we wanted to do was, let's say that, pretend that we're a user or someone that we've collected this data and we've identified these two hotspots. Now we want to look at the neutron energy spectra given off by each one of these sources. So for this analysis, we just define two regions. These are arbitrarily defined regions around our source. And you can see region 1 and then region 2. We then developed the methodology for how do we assume that a cone projection actually came from one source or the other. So to do that, you can see here at the bottom, I have 3 figures, and these are 3 separate cone projections. And this details our methodology for determining if a cone projection counted for a given energy region. So we can see the basic criteria was if the cone overlapped where at least greater than 90% of the amplitude of the cone overlapped with one of these boxes, we counted that cone projection towards the net energy spectra we were looking at. So we can see here a cone projection that would count for region 2 and a cone projection that would count for region 1. We also performed some analysis to see what happens if a cone projection overlaps with both regions. And we tried doing a relative intensity comparison or something of that nature with the overlap, but because we defined arbitrary regions, that didn't necessarily pan out so well. So we decided, and what ended up working the best, was if we have a cone projection that overlaps both areas, so what we see in this bottom right image, then we just remove that cone projection entirely and we don't add the energy deposit or the energy interaction from this cone projection to our net spectra. In addition, if we get a cone projection that doesn't overlap any of the regions, we also throw that cone projection out and do not look at it for the purposes of this analysis. So applying this methodology to our simple back projection image, we obtained this result. So you can see here, we have our sum spectra. So this is all events that interact with both regions. And then we have our region 1 spectra and then our region 2 spectra. So just to look at bulk information for region 1, we see that it has an average neutron energy of about 3 MeV. And then for region 2, we see an average neutron energy of 4 MeV. And from the simulated spectra, pardon me, we know that the californium-252 source has a softer spectra than the plutonium-beryllium source. So this lines up very nicely that it looks like we're able to identify the two sources, since the second region, which we know is the plutonium-beryllium, has the higher neutron energy spectrum. However, we wanted to verify this and validate it. So we re-performed the measurement in the exact same geometry. However, we only did one source at a time, and we performed the exact same analysis on this. That way to see, can we isolate these spectra with the individual source spectra? And that's what I have right here. So let me take just a little bit of time to go through these plots. So on the left, this is comparing for the californium-252 data. We can see in blue here, this is the extracted spectrum with both sources present, region 1. This is the data that you saw on the previous slide. We then have the extracted spectrum in orange when only the californium-252 source is present. And we can see that this matches up relatively well within uncertainty with that, which means the majority of our events that we are getting in that region are actually coming from the californium-252 source. Now, something to note here is that we also have the extracted spectrum from only plutonium-beryllium. So we also looked at this region when we only had the plutonium-beryllium source present. And we can see that we do have some cone overlap where interactions that we know came from the plutonium-beryllium source do count towards the californium. But comparing this spectra in gray here with the spectra in orange, we can see that the orange spectra is dominating, which is very good, which means most of our information is coming from the Californium source. And we did the exact same thing with the plutonium beryllium that you can see over here, where we have the extracted spectra in blue, and then we also have the extracted spectra from only the plutonium beryllium source there in gray. And we can see that these are both also relatively within uncertainty. And we do have some overlap where we do have some events coming from the California that do end up counting towards our extracted spectra. However, we can see that the true extracted spectra are dominating, and thus we can identify and use spectroscopic capabilities to identify these two sources. So what are some of the MTV impacts of this work? We've had the opportunity to perform measurement campaigns at the Device Assembly Facility and Idaho National Laboratory. Neural Shaw showed an image that had the H2DPI on the opposite side of it, where we had our MOX fuel canister and then plutonium plates surrounding it. So we intend to take this methodology and apply it to those measurements of special nuclear material to see if we can identify a plutonium oxide spectra versus a plutonium metal spectra. And then also a big shout out to Sandia National Laboratories for Pete Marlowe, who has helped with some of the imaging methodology with this work. And then we're also collaborating them, as Nathan showed you, for the organic glass. So in conclusion, one of the things we wanted to see was, or test the spectroscopic limits or spectroscopic capabilities of this handheld system, which is a very compact system, to see, even in such a small system, can we identify and differentiate sources based off of the extracted neutron energy spectra. And at least with the Californium and plutonium beryllium, we have shown that yes, we can. And then some future steps. We are currently developing a 16-pillar system that incorporates cerium bromide into the system. And you can see that I have a VisEd rendering of that here. So with that, I'd like to thank CVT, MTV, and DITRA for funding this work and supporting this work. And I'd be happy to take any questions.
Thanks, Will. Very nice talk. We've got a few questions in the chat here that I'll go through. The one I'll ask first is about the total efficiency of the system, specifically to a watt spectrum.
So the total, so I believe with this system, it was something on the order of 0.0, I believe it was 0.0, less than 0.01%. I don't remember the exact number off the top of my head, but for neutron double scatter efficiency, it was on that order. In a theoretically fully developed system, based off of simulation models that have been done, we believe that the system would have upwards of about 0.6% intrinsic efficiency.
What do you mean by fully developed?
So if we were to, instead of just having 7 still beam pillars, if we were to have 64 still beam pillars coupled to the complete SIPM array.
Mm-hmm. Great. There's a question about applying this system to oil well logging applications where they use immersing beryllium sources on the order of 16 curies. Could you talk about how the system can image those sources?
That's a very interesting question. My initial reaction is a 16 curie, well, I'm not entirely certain what the neutron intensity off of that would be. This system could absolutely be used to image those neutrons. I'm not familiar enough with those oil systems to know how it could be used or developed, but yes, if you require a system that is capable of imaging neutron sources, this is absolutely a system that can do that.
Yeah, the PUBI in our lab's is 1 curie, so this is about 10 times more than that, roughly. So good. How about the total cost of the system? Can you speak a little bit about the components of the system? And
of course. So each SciPM array is about $3,300. Each still beam pillar, I believe, last time we purchased them was about $400. So our in total system is in the tens of thousands of dollars currently. We are looking, right now we use Kane digitizers for the acquisition. We're actually looking to start a collaboration with the Space Research Laboratory here at the University of Michigan to develop an ASICs or FPGA system. So that will make a much more compact system than using those digitizers and be able to read out our data that way. In terms of cost of those, I do not know.
Great. So you showed results for spectroscopy of californium and PUBI, right?
Yes.
Yeah, and then so Justin's asking, do you have data or do you plan to measure any sources that are a combination? So like a plutonium oxide source, which would have both a fission component and an oxide component, and see how well the system does in those applications.
Absolutely. So as I briefly mentioned, we performed a measurement at Idaho National Laboratory where we measured a mixed oxide fuel or plutonium oxide sample, and then also had plutonium metal in the same field of view. So we intend to apply this methodology to that measurement to see if we can differentiate the plutonium oxide spectra from the plutonium metal spectra, which should give us, which the plutonium oxide spectra should be an alpha N plus spontaneous fission, and the plutonium metal should just be the spontaneous fission.
I think I grabbed everything from the chat. So if anybody has a question they want to ask, please feel free. Go ahead and unmute yourself and ask away. Okay, I have one. I had a question about the regions you defined. So I think you mentioned that those regions were arbitrary, which is fine. I'm wondering if you did any sensitivity, like how much do the spectra change if you play with the size of those regions?
I have not, but that is something we are definitely going to look into to make this a more robust system. Because there's probably some optimization we can perform looking at the spectra, the overlap, and what is incorrectly counted towards one region versus the other.
Yeah, can you go up to the image, the regions?
Sure.
Yeah, so you basically just drew a box around the back projection kind of by eye?
Yes.
Yeah, okay. Great. Okay, well, if no other questions, we'll thank Will for your great talk and ask you to release your screen.